And we will start with a keynote talk by Professor Steve Wofsy from Harvard University, who will tell us about global scale measurements and modeling of CO and pollutants in the atmosphere tomography mission, exploring the atmosphere where pollution goes to die. So that will be an interesting talk. So please join me in welcoming Steve.
It's such a pleasure to be here. Thank you very much for inviting me. Can people hear all right? Is this the microphone? Or is this the microphone?
Don't get too close to the mic.
Okay, don't get too, okay. So, you know, the title on your program is kind of generic, and yeah, we're not doing that. So after some thought, I believe it's time for us to really start to consider how to quantitatively use the atmospheric tomography experiment data to really begin to understand the atmosphere. And GSChem is going to turn out to be a wonderful, wonderful tool for doing that. So the idea behind this experiment was to study the most remote parts of the atmosphere. And I put up these two definitions because I frequently hear people talk about the pristine atmosphere. So the Go Amazon project, the atmosphere is pristine in the Amazon and the Central Pacific Ocean or the Antarctic or the Arctic. And of course, it's not really true. You can see the impact of human activity, human emissions everywhere. And we can in particular see them out in those most remote parts of the atmosphere. So the experiment was designed to try to assess what those impacts are quantitatively. And boy, did we get some surprises. So I'm going to tell you about one in particular I'll focus on, but let me just give you a little bit of a kind of general introduction to the mission. So we used the DC-8, so-called flying laboratory. I love this picture of the DC-8. It's a really, really old airplane. If you get far enough away from it and the paint has been refreshed recently, it looks kind of nice. But it has many advantages. In particular, it's very, very robust, and it's been used for these purposes for a long time. So most of the systems are well developed. We were very, very concerned that we would have significant interruptions due to the age of the aircraft and whatnot. And actually that never happened. There were a couple of close calls, but that never happened. And the idea is to go around. Can we see a pointer here? Maybe a laser pointer. Yeah, the idea was to go from California down to the equator on a first flight, which is a flight that is intended also as a kind of your last test flight, and then up to the Arctic, down the middle of the Pacific Ocean, across the Southern Ocean, which it turns out you can only do that flight in one direction because of the winds. It's too long to do it in any other direction. And then you have to land in Punta Arenas and hope that the weather is okay there for landing. And then up the middle of the Atlantic Ocean to Greenland, and then across the Arctic back to Alaska and back down. So we basically circumnavigate the globe 1.5 times. This is another view of the mission. So yes, just one other thing. During the entire time, the plane is going up and down. So that's it's trying to take a slice out of the atmosphere. There's 5 minutes at the bottom, 10 minutes at the top, and then up and down and up and down and up and down. So you get 2.5 or so of those up downs per hour. This is another view of the flight track. I drew it this way because I wanted to emphasize the fact that here in the tropics, where we have easterly flow, we're actually flying down here, upwind of here, about a week or week and a half before we get to the Atlantic. And that turns out to be handy because we're going to see some really amazing things happening here in the Atlantic, and we want to think about, well, what is the inflow? Well, we just characterized the inflow. We were just actually right there. The 4 missions were in August of 2016, February of 2017, October of 2017, and May of 2018. So it covers 4 seasons. The idea was to get an ensemble. We don't do any plume chasing. We don't do any plume avoiding either. It's just a straight shot, weather permitting. So now I want to focus on the tropical Atlantic. And this was a really bit of a surprise for us. So this is a cross section going from Punta Arenas all the way up to Greenland. And in this zone of about it's about 20 to 30 degrees of latitude in the tropics, depending on how you want to count, you have extremely intense pollution, which is originating in the African continent. Depending on which way the wind is blowing and how you want to measure, you're about 3,000 kilometers from the source. And you have concentrations here of 300 ppb or more of CO. Another thing to notice about this is that this material does not intersect the ground for the most part. There is pollution at the ground, but if you're looking at data from ground stations, you generally won't see this. You won't see most of it. Another thing to notice is that it goes all the way up to the top. And that really surprised me. It probably shouldn't have if I'd looked more closely at what the winds are doing there. But I had expected this to kind of be limited to the trade wind inversion and below, and that is not true. This is a picture of the, I guess you can't see it for the most part, but this is an image that we took on our first flight. Come on, where's the cursor? No cursor. But you can see that from aloft you could actually not see the surface of the ocean due to the pollution aerosols. So this one here is for ATOM 1. This is for ATOM 2. Once again, you can see this bolus of stuff. It does not intersect the ground, and it goes all the way up to the top. Now let's go and just take a little bit of a survey of this before I try to get into some of the some quantitative analysis. So here again, I've shown at the upper left-hand corner the CO cross-section, and on the bottom I have two representations of black carbon in the same cross-section. The one on the left is from the GSFP, or forward process model, and the one on the right is what we actually observed. And what you can see is that the black carbon, as represented in the GSFP, is really, really good until you get to about 3 kilometers. And then in the atmosphere, the black carbon is basically starting to be removed. By the time you get to 4 kilometers, it's gone. And the model does not reproduce that by any means. So the model result looks a lot like the CO. The atmospheric measurements look really quite different. And you can also see that, depending on how closely you want to look, that the black carbon is actually a little wider than the CO. There's a lot of other little interesting things that we don't have time to discuss. So now this is all 4 of these cross sections. The top is the Atlantic. August, February, October, and May from left to right. The bottom is the Pacific. And you can see that with the exception of ATOM 3, the Pacific is very, very clean. It's not too difficult to get a background. For the ATOM 3, there's just one heck of a lot of pollution in the southern South Pacific, and that actually goes all the way to Antarctica, 88 south. So it's quite an amazing phenomenon, subject for another day. Okay, so this is now the zonal winds, and what you can see is that the easterlies extend all the way up to 10,000 meters, so I shouldn't have been surprised to see the pollution there. The width of the easterlies is about the same as what we observed for that large amount of pollution, and so well, I can actually do a little calculation. I can, first of all, I can use the Pacific measurements to get a background. And what I see is that in the South Pacific, the background is basically 50 plus or minus a little more ppb, with the exception of ATOM 3 in October, when it's 15 or 30% higher. And so that was a little bit of a surprise. And the other thing is that we can look at the South Pacific, the North Pacific, come up with very good representation for what we think is flowing into the tropical Asian area and then eventually into Africa. So it's of order 50 to 60 ppb. Now we ran the stilt footprint model to try to understand the distributions that we observed. And it turned out pretty well. It's being driven by the GFS. And at the lowest altitude, so shown on the upper left, the air actually doesn't come from Africa. It comes from the South Atlantic. And that's why you tend to see much cleaner air right near the surface. That was kind of a big surprise for us, and it was basically observed in all of the missions. So you certainly do see pollution from Africa in the lower altitudes, but it's been strongly diluted by air that's coming straight from the South Atlantic. When we go into those middle altitudes, 2,100 meters, 3,800 meters, you can still see South Atlantic influence, but also Central African influence. And then we go up to the very top, you see something quite different. You see deep convection to the south of this influence area here. And I'm amazed that the GFS captures that. So if we now try to map those footprints onto emissions, we get these emissions from Eloise Murray, who has done a very detailed study of African emissions. This is for 2012. So we'll have to do them for 2017. And what we see is that, yeah, this guy here and that one is picking up the main area of biomass burning across Africa during this particular season. It moves around and we pick it up likewise in the other seasons. And this one is picking up an area where there isn't any biomass burning. Maybe you can't see it because it's raining. And probably the model doesn't have quite enough inflow in the boundary layer because it predicts a pretty small enhancement. This is now the just taking those footprints and applying them to Eloise's source model. And so the red curve is what we predict based on her models. That's our prior emissions multiplied by the footprint. And the black is what we observe. If we multiply the red by the enhancement by 2, we basically get the observations in the lower part. The upper part, not so much. And so what I'm not clear on at the moment, and we will eventually figure it out, is whether this is actually coming from Asia or whether it's coming from Africa and just not being well represented by the model. Okay, so next thing to do is to actually try to interpret these data quantitatively. So if I take the elements of those, the measured westerly winds and multiply by the observed enhancement of CO, I can calculate the flux. So that's what I'm going to do. So that's actually an indicator of the flux in some units like kilograms per meter squared, where that's meter in the horizontal, in the vertical rather. That's going across a plane that's north to south at the longitude of Ascension Island, roughly, and that basically gives you the flux. And so we can integrate that to get the total flux. But you can see that, yeah, it looks pretty good. And we integrate it starting from the south to the north and look at the cumulative amount, and you have the total emission passing through this part of the atmosphere. And it's an astounding amount. So on an annual basis, each of those missions is giving something like 200 to 270 or 280 teragrams of CO2 per year, the exception being ATOM 4, where the enhancement was about half as much, about an annual rate of 100 teragrams per year. And we can compare that to Brian Duncan's budget. The best budget I could find, maybe there's a more recent one, but it looks pretty good. So we're saying that, roughly speaking, ATOM is seeing emissions of CO of between 200 and 250 teragrams per year from this just going through this one sector. That's about half of global biomass burning emissions, according to Brian's table, and maybe 20-25% of global emitted CO. So it's not that much of the global budget for CO, because CO is also produced photochemically. But if we want to compare that to other primary emissions, that's kind of the number to look at. So something like 20-25% of emitted CO. So we have a lot of species on ATOM, 600 or so. And so I just said, well, okay, let me just run through these and ask how many of the 600 parameters that we're reporting have a significant correlation coefficient in this area with CO? And the answer is about 200. we have a pretty good way of estimating emissions that are coming from this same large continental scale area for lots of other things. So there's benzene, ethane, acetonitrile. You can see that it's quite remarkable. This stuff is very, very distinct in the Atlantic, and you really don't see much sign of it in the Pacific. So it does not manage to get across the Andes, basically. It gets to South America, but it doesn't really get across the Andes. It goes somewhere else. Maybe it gets mixed. Maybe it gets turned around, go down to the South Atlantic. It's a little hard for me to figure that out. So there I go. I have a whole bunch of these. All right, so here's acetonitrile and HCN plotted against CO just for this sector, just for ATOM2 as an example. It's a pretty good correlation. So I can take the slope of that line and estimate the total emissions of acetonitrile and HCN for those particular flights. And I get about, let's see, about 35% of global sources according to Xinbin Li's paper. That's the best I could find for a budget for these two compounds. Maybe so about the same fraction relative to the CO biomass burning, maybe certainly that order, 30 to 35%, 37% for HCN, and a very good number. So we can keep going with this. 2 minutes remaining, according to Dylan, and I am actually about on time here. If I look at ethane, I'm going to find about 10% of the ethane emissions globally, according to the, I didn't write down whose budget that was. And that is basically telling us that, oil and gas emissions, while potentially playing a role, probably not much. That 10% is probably about what you'd expect from biomass burning itself. For benzene, somewhat different. Okay, let me sum up. ATOM sampled the most remote parts of the atmosphere. And it's really a beautiful, beautiful data set for satellite validation and for GS Chem studies. And I know a lot of people in this community have already been using the data. They're all public except for ATOM4, which is partly public, and the rest of it's going to go public at the end of this month. So it's all out there for people to use. We transected the mid-Pacific and mid-Atlantic, nearly pole to pole. We found really intense pollution from Africa and almost certainly some contribution, especially at the higher altitudes, from tropical Asia. This was not totally unexpected, obviously. This is an area that's known to be affected by pollution, but because a lot of this pollution does not actually intersect the ground, I'm not sure that we had a particularly good idea about how much. And we were able to quantify based on those data. The emissions from Africa were within the large uncertainty estimates for biomass burning sources. I think that's we will be able to refine that. We could leverage the CO budget to get continental scale regional estimates, regional emission estimates for a lot of other species. And I'm hoping that this is of great interest to this community. And so what we found for the ones I just looked at, which was just over the last week, that, roughly a third of global emissions appears to pass through this really small area of the atmosphere for those species that are originating in this type of activity. And then finally, I think Lagrangian transport models really worked very well in this case to help identify where the emissions were coming from. I think they make an excellent complement to the GS Chem approach, and I hope to see people adopting both of those. And now I'll take questions. Am I on time, Dylan?
Are there any questions for Steve?
Steve, if you look at the budgets that you're estimating for these different species, like do the ratios relative to CO agree or not with sort of what we would predict from biomass burning kind of emission inventories and ratios that we would use in our models?
So I think the answer is yes. I think the activities are higher than what's in most of the models, and the ratios are about right. So when I look, for example, like Schorner-Bansky has a paper where they did all the stuff on the burning table for different types of materials. The ratios appeared to be right on the money. Another thing that I was really surprised about was that we had two different ways of estimating what the activities might be, how they might be adjusted. One was using the footprints I got about a factor of 2. And the other was just using this total flux approach, and I got about a factor of 2. They're completely independent, actually. So, so my thinking is that the main difference is the activities. Good question, though, Dylan. Yeah. Chris?
Sorry. First, and then we'll go back.
Oh, so building on that, do you see plumes of anything besides biomass burning coming from Africa?
Absolutely, we do, but they're hard to piece out because of the overwhelming size. But there's clear evidence of oil and gas emissions, and Eloise will tell you that she can see the signature of charcoal burning. So, so we obviously have some refinement. When you have such a big signal, it's hard to pull out. But you can definitely see some compounds that are elevated in some parts of that plume and not in others. I didn't have time to go into this, like some of the alkyl nitrates that would be indicative of industrial or oil and gas.
Steve, in terms of the transport of biomass burning from Africa, there's also recirculation that sends it in the other direction, right? So in terms of your flux estimates compared to source estimates, doesn't that have to be taken into account?
Absolutely, it does. And so when we write a paper about this, we will try to estimate that. But I think we have a very credible set of prior emissions locations. So the locations seem to be quite good. So I think we should be able to estimate what we're not seeing that's coming out of Africa. And so absolutely that would be part of it. But it's not going to lower my number. It'll raise my number.
Do you have any evidence on those, how old or fresh those plumes are?
Yeah, Roisin has looked at some of this. She's one of the principal co-authors here, and she has. You can talk to her later about it, but she has said that the stuff higher up is clearly older, consistent with potentially an Asian source. I know Roisin is out there. You might comment on that somewhere. Yeah, so there is, you can see different ages at different locations.
Okay, please join me in thanking Steve again. Our next speaker is Scott Miller from Johns Hopkins, who will talk about recent trends in methane emissions from China and opportunities for mitigation.
Thanks, Dylan. In the next few minutes, I want to talk with everyone about some work that we've been doing with Geoschem, specifically to understand methane emissions from China and to explore some opportunities for mitigating those emissions. And before I move on, I just want to mention that this has sort of been a collaborative work with a bunch of different people. First of all, as many of you probably know, China is most likely the world's largest emitter of anthropogenic greenhouse gases, both carbon dioxide and methane. And here's a plot of the EDGAR inventory, which I know that many of us have used in the past, showing global methane emissions. And what you can see pretty immediately is that China pops out like a blue light special over here on the right-hand side of the map. And unlike countries like, for example, the United States or many countries in Europe, one of the largest sources of methane emissions in China is from coal mining. And just to clarify, that methane is emitted when the coal is mined, when mining companies excavate and when they extract the coal from the ground, the methane that was trapped in that coal seam then gets released to the atmosphere. There's relatively minimal methane that gets emitted during the coal combustion process. However, this picture related to China's methane emissions, and specifically methane emissions from coal, could be changing quite substantially for a number of reasons. First of all, the coal mining industry in China has consolidated substantially over the past 15 or 20 years or so. There are about 10 times fewer mines today in China than there were 15 years ago, because the coal mining industry there has been consolidating into a relatively small number of large state-operated mines. So the structure of the industry is very different from what it used to be. Secondly, there are a number of new coal mining methane regulations in China. Many of these are targeted at safety, but could also have substantial impacts on the country's methane emissions. As of 2006, China required that mine operators have to drain all methane from the coal mines before beginning mining operations. And I think that was largely out of safety concerns. As of the early 2000s, there were about 2,000 coal mine-related deaths in China every year, and many of them were due to mine explosions due to methane. And by 2010, the government said that all operators of coal mines, they've either got to use this methane, i.e. use it for electricity production or heating, or they've got to flare the methane to produce CO2, thus mitigating those methane emissions. So just because of these regulations alone, we should be seeing large changes to China's coal mining emissions. And then third, the country's implemented a number of different incentives to encourage the use of methane for electricity or for heat production. For example, any methane from coal mining that's put into, that's combusted to produce electricity, that electricity is required to receive priority on the electrical grid and is required to receive a minimum price. So all in all, these incentives and regulations are quite ambitious. The national government has set that by 2020, they should be utilizing about 14 teragrams of methane per year, either for electricity or for heating. 14 teragrams is almost half of total US methane emissions. So this is a pretty substantial number and would not only have a big impact on China's emissions, but also could have an impact on global methane levels. So we wanted to look at this question in greater detail. So we constructed some methane inversions using GOSAT observations from 2009 to 2015, and then also using simulations with the GeoSchem model. And we wanted to understand recent emissions trends and also try to get into what the possible causes of those trends could be. And here are some initial results of what we found. And let me walk everyone through this plot. The x-axis shows year from 2000 to 2015, and the y-axis shows total methane emissions. The black line up there on the top is from the EDGAR inventory that we saw earlier. The red line on the bottom is the estimate from US EPA. And then the blue lines there in the middle are several inverse modeling studies from previous time periods. One's by Peter Bergamaschi and the other's by Rona Thompson. And then the green is what we estimated using GOSAT observations for 2009 to 2015. And if you look at Rona and Peter's studies on the blue, they estimated that emissions from China were increasing by about 1.1 teragrams of methane per year. When we did this study, we thought that we'd see substantial changes in China's methane emissions and growth in emissions between 2010 and 2015. But lo and behold, when we estimated for more recent time periods, we found that methane emissions were also increasing by 1.1 teragrams of methane per year. So this reduction of China's emissions by 14 teragrams of more, if it happened, we definitely didn't see it in the atmospheric observations. And we also did some work to try to understand where these emissions were coming from and why these changes were happening. And we looked at both economic statistics from China and other factors. And what we found is that, without going into detail, that these emissions increases are most likely coming from the coal industry. So our conclusions, though, are that emissions from China seem to be continuing to increase at similar rates as before these regulations were put into place, that emissions trends appear to be driven by coal, and that if these regulations are having an impact, we're not finding that impact. So Mingyang Zhang, who's a PhD student at Johns Hopkins, has been doing sort of a follow-up or next step and looking at how could China use this methane to support air pollution policies, and what co-benefits would those methane emissions reductions have for air quality and health? Again, the national government may not care as much about greenhouse gas emissions reductions or methane emissions reductions, but they certainly do care about air quality. So how would this work? Mine operators could capture that coal mine methane, use it for electricity or home heating in place of coal, and then finally that reduced coal burning could lead to potential air quality improvements. And here are some initial results that Mingyang found. Again, these are using nested geochem simulations across Asia. And what she found is that if China met its 2020 goals, that you'd see a PM2.5 reduction over there on the left-hand side. And on the right-hand side is sort of her best case scenario. What would happen if China were to use all of this methane in electricity or for home heating production? And in this scenario over here, again, this is sort of defining the edge of the envelope. She estimates that these reductions in PM2.5 could be in the range of 10 to 15% of ambient PM2.5 levels. So relatively substantial. And then lastly, the sort of current plan, the project that she's working on right now, China's implemented something known as its Clean Winter Heating Plan, which calls for eliminating in-home coal heating, and has specified that about 70% of northern China should use clean heating by 2021, i.e. sources like natural gas. And as many of you may have heard in the news, this has left some people in northern China literally out in the cold over the past couple of years. And so that's our project at the moment. And with that, I would love to take any questions that people might have. Thank you.
entered flares or threshold that's maybe causing they're not producing enough to actually have to follow that?
Yeah, one thing that I find really interesting, if methane is present between about 5 and 15% in the coal mine gas, that gas can be explosive. If you get methane higher than about 15%, the methane content is high enough and the oxygen level is low enough that the gas is not explosive. So the Chinese government has said that if the gas coming out of the coal mine is under about 30% methane content, that those mine operators are exempt from following any of these regulations. And EPA at least has said they have reason to believe that what these coal mine operators might be doing is simply just diluting the methane content of the gas down, which not only makes this gas unusable, but also makes it explosive and potentially dangerous.
In the air quality assessment of the benefits of displacing coal use, have you considered also including the benefits of displacing biofuel sources that might have an even larger direct PM2.5 source?
I think that's a really great point. So Mingyang at the moment is looking at the co-benefits of replacing like in-home coal use, but I think biomass would also be a really interesting thing to look into as well. I think that's a great point.
I know there are a few other questions, but please, you can talk to Scott during the break. Let's thank Scott again. So our next talk is by Yushan Zhang from Harvard, who will talk about the global budget of atmospheric methane as inferred from GOSAT satellite observations during 2009 and 2017.
Good morning. I'm Yuzhong Zhang from Harvard. Today I'm going to present some results from a global inversion analysis from satellite observations of methane from 2010 to 2017, where we try to use GOSAT satellite observations of methane to resolve the global budget and the emissions of atmospheric methane. As we all know, methane is an important greenhouse gas, and its concentration, according to ice core record, has been increasing since the pre-industrial time. And this increase is quite fast, but we do not fully understand its evolution. Part of the reason is that a lot of anthropogenic and natural sources contribute to the emissions of methane and makes its emission profile quite complex. On the anthropogenic side, fossil fuel, landfill, ruminant, as well as rice are all very important emission sources. And on the natural source side, wetland is a predominant natural source of methane to the atmosphere. And the methane is removed predominantly by tropospheric OH, which gives it a lifetime about 10 years. Our lack of understanding of methane is probably demonstrated in our difficulty to explain the methane evolution in the last 30 years, where we see methane increase stops at around 2000 and level off until 2007, it starts to regrowth. Here we are trying to use satellite observations of methane to better understand the global budget or emissions of methane. Methane can be measured by the satellite through solar backscatter, where methane column mixing ratio can be measured and retrieved at 1.65 and 2.3 micron. A good strength of satellite observation compared to the relatively sparse surface measurements is satellite has a very good global coverage. So it allows us to resolve the spatial distribution of methane emissions. So my former colleague, Brown Masakas, has done a brilliant job, set up a global inversion to infer a global distribution of methane emissions from GOSAT observations between 2010 and 2015. And the work I'm presenting today is primarily based on his previous work, with a few improvements that I will detail in a few slides. Also, owing to the good coverage of satellite observations, we found we have there's a potential that we can use satellite observations to not only resolve the methane emissions, but also have some constraint on the global mean OH, which is a predominant sink for methane in the atmosphere. Besides its advantages, satellite observations also has some difficulties. Compared to the ground measurements, it's relatively imprecise and inaccurate. Also, there's a large amount of satellite observations. We have to use a model to interpret those observations. And we know model also has its own problems and which leads to the errors and the bias. So for inversion to work, we have to account for those errors or biases. Also, to interpret the satellite observations, we need to have a very good prior information about methane emissions, so we can resolve to interpret the co-located methane emissions. This slide shows the framework we have, which is set up in the Brown's work. Basically, we use geoscam simulations to bring together the information from prior emission inventory, satellite observations, and varied error specifications. With geoscam, using geoscam, we simulate the prior methane vertical columns and compared it with the satellite observations. In addition to that, we also use geoscam to construct the Jacobian matrix that is used in the inversion, which is basically the sensitivity of column methane concentration to the state vector that we want to optimize. So here we want to optimize the state vector we want to optimize is the annual mean emissions and its 5-year linear trend on the 4x5 degree grid cells. And in addition to that, we're also trying to optimize for annual mean global OH. In this work, we have made and implemented some improvement on the framework I presented in the last slides. First, we implemented the best available prior information we have. Most noticeably, P.S. Capelli has compiled a global fuel exploration emission inventory that we think has a better or precise information about the oil and the gas and the coal emissions. Second, we also improved the stratospheric bias that is we know to present in to exist in the geoscam model simulation using the independent satellite observations from ACE-FTS. And the most significant improvement in this work is that we have a better treatment for wetland emissions. Basically, I will detail this improvement in a few slides, but basically we are trying to separate out wetland emissions and non-wetland emissions and trying to optimize them in different time and spatial resolution. So in the previous version that Brown has set up, inversion is performed on each 4x5 degree grid cells for optimization of annual mean emissions as well as a 5-year linear trend on those 4x5 grid cells. This has several problems. First, we only optimize for annual mean emissions. That means we have no mechanism to correct for the prior seasonality, which means we assume the prior seasonality is correct. But we know that seasonality in prior wetland emissions is very uncertain. Also, on the 4x5 grid cells, we do not account for the fact that wetland emissions correlate with each other spatially within a large region because they are driven by the same environmental factors. and we are not using this information in our inversion before. And third, we are trying to optimize for linear trend. This is okay, probably okay for anthropogenic emissions, but it's very difficult to justify for wetland emissions. In this version, we only perform this for non-wetland emissions. And for wetland emissions, we optimize them for 14 subcontinental large regions, and we optimize them for monthly mean emissions. So 14 subcontinental regions is shown in this figure. And this means we should superimpose the spatial correlation within these large regions. And also, for the monthly mean emissions, we allow for the correction for seasonalities. This slide shows some initial results from this inversion. First, we evaluate with our result with the goal set, the training set we use. We can see in the prior, there's a large errors on the global mean, as well as latitudinal bias. Each line represents for different latitudinal means. And we can also see a large seasonal bias from this prior figure. But in the posterior, after we optimize with the goal set observations, we can see these biases are largely reduced. What's more exciting is that when we evaluate it with our posterior with independent ground-based observation from TCON network, we can see all over the world from south to the north, and the errors in the prior simulations are largely reduced, which is here prior is shown in the blue and the posterior error is shown in red. And when we decompose this total error into different components, we can also see the seasonal bias is also reduced. Sorry. Yeah, so this is our result for different budget components, including wetland emissions, OH loss, and the non-wetland emissions. We can see a lot of interesting feature here that was more closed up investigations. And we also compare our result with the. Okay. Yeah, this is my summary. I will leave it here.
Okay, thank you. Please join me down during the break. Our next talk will be by Diana Picosa from the University of Wollongong, who will talk about an improved carbon greenhouse gas simulation in GSCAM.
Towards unimproved.
Towards.
Awesome. Yeah, so today I'm going to talk about a new simulation in the GSCAM that will be included in the forthcoming versions of this model. So the new simulation focuses on the carbon greenhouse gases, carbon dioxide, methane, and carbon monoxide. As we all know, these gases are pretty important since their atmospheric amounts have grown dramatically since the pre-industrial revolution with significant impacts on our climate. So carbon dioxide and methane are the two main direct greenhouse gases, while carbon monoxide has an indirect impact. Now, in addition to the primary sources and sinks of these gases, they are also chemically dependent, which means that changes in the atmospheric amounts of one of these gases can have a great impact on the others. So briefly, in the atmosphere, we have methane that oxidizes, creating CO, that again oxidizes, creating carbon dioxide. Now, in the current GeoSCAM simulation, we have a standalone or so-called specialty simulation for each of these gases. However, since they are standalone, they're also decoupled, which means that this chemical interaction is not included directly in the simulation. So the aim of this work was to create a new simulation by coupling the three decoupled carbon greenhouse gas simulations. So why would we want to do that? Well, one, hopefully for a more accurate simulation of these gases. And secondly, this simulation can also be used in inverse modeling of satellite observations of these gases to constrain and quantify the different carbon fluxes. Now, if you look back to what's actually happening in the atmosphere, in the uncoupled versions of these models, we have the methane simulation that has literally nothing to do with the other two simulations. which means that the chemical production of CO from methane is actually calculated in the full chemistry simulation and used as monthly average archive fields in the CO-only simulation. And same goes for carbon dioxide. Now, in the coupled simulation, we use the methane part to calculate the methane loss by OH, and then we pass it to the CO part of the simulation as the CO production of methane, and we switch from an offline to an online calculation of the source type. And then from CO, we calculate the CO loss with OH and pass it to the CO2 part as the chemical production of carbon dioxide. Now, the two main fields that will be impacted by these changes are the CO production from methane and the CO2 production from CO. However, we also added an additional update to the methane part of the simulation, which is that we now include an OH diurnal cycle that was not included in the offline methane-only simulation. So these plots show the methane loss by OH without the inclusion of the diurnal cycle at the top and with the inclusion on a daily scale. And what we can see that actually there's not much difference between the two. However, if you look at an hourly scale now, we can see some significant differences because, as we all know, methane loss by OH before was basically happening everywhere, 24 hours a day, but that's actually not quite accurate due to OH availability. Now, the rest of my results will be focusing mainly on the CO2 chemical production term. So on these plots, we can see the total column CO2 chemical production source from the uncoupled simulation, from the new coupled simulation, and the bottom is the difference between the two. And this chemical source is, in contrast to the other CO2 primary sources, it's not a surface flux. It's a 3D source. It's happening everywhere and produced everywhere in the atmosphere. So we're looking at total columns because it is the most representative term to analyze the changes of this source type. So the overall budget from the coupled simulation is lower relative to the uncoupled simulation, which is highlighted by the orange regions in the difference plot. But however, we also find some regions where the chemical source of CO is actually a lot higher relative to the uncoupled one at South America and Africa. Now, relative to the total CO2, the chemical source is around 10% of the total CO2 source, which is actually quite significant, and it's not a term that could be easily ignored. Hence, the improvement of its simulation is quite important. And this is especially true in regions where primary CO2 emissions are quite low, and this production term can actually contribute significantly to the total CO2. Now, if we move on from the yearly picture to the month-to-month picture of the CO2 chemical production only, so this is not the total CO2, we see that between the uncoupled and coupled simulation, we have a similar spatial distribution of the source, which is awesome. However, the differences for all months, again, highlight a couple of regions, South America, Africa, where the chemical source is actually potentially a lot higher than we thought before. However, the main difference between these two simulations is actually mostly highlighted when we look at higher temporal resolution. So as I said at the beginning, in the uncoupled simulation, the CO2 chemical source is based on monthly average files from the full chemistry simulation. This means that the day-to-day change or hourly change of this source type is only driven by transport, which is shown on the top plot. However, now in the coupled simulation, this source is actually updated at every simulation time step relative to the CO loss, which means that we can actually now check the changes of this source type and higher temporal resolution. As, for example, we can look at the diurnal cycle, which is basically just a flat line in the uncoupled simulation. And this is also important in case of inverse modeling if we use observations that have a higher temporal resolution. Now, to wrap up, so the next step with this simulation is to validate it both with surface and column measurements. And we plan to use a new simulation in the future to look more in the spatial and temporal variability of the different source of chemical production terms, and of course to add it to the GeoScam adjoints to do some fun inversions. Thank you.
Questions for Liana?
Liana, would this chemical source of CO2 contribute significantly to the diurnal variability in column CO2?
Yes. it's not shown here. I have looked at it, but yeah, we can chat about it later.
It does.
if you want.
It's something
Yeah.
people should worry about.
Well, yeah, it depends on the region where you look at, because I mean, if there are strong primary sources, it won't really contribute. But I found some regions where they're really low primary source. In that case, it actually contributes a lot to the total CO2.
Any other questions?
So it sounds like you're using static loss fields for methane, but that neglects the methane OH feedback. Have you considered trying to account for that and couple that in? Because that's an important source of methane variability.
Yeah, it's an important, we did think about including an OH feedback. It would be really interesting to see a methane OH CO feedback between these gases, but it's not included, but it's one of the future directions of this work.
Any other questions? Okay, let's thank the editor. Our next speaker is Kevin Bowman from JPL, who will talk about resolving information in large-scale inversion.
First of all, I want you to know that you are special. Very special. This group, unlike anyone else in history, has experienced carbon dioxide concentrations at this level. Not since the formation of Homo sapiens 350,000 years ago, not since the migration from Africa to North America, to Europe 63,000 years ago, nor since the formation of modern human civilization 10,000 years ago has anyone seen this much CO2. And nobody is going before us will experience the climate that is to come. That consequence is sufficiently terrifying that has led to the landmark Paris Accords. And an important component of that Paris Accord is something called the global stocktake. It's every 5 years, starting in 2023, I believe, where different countries will pull together, try to assess what our carbon is and how climate is changing to determine whether or not we're on track, whether or not we need to change. But there's a fundamental question that has to be addressed. That is, what is the relationship between emission commitments, which is what carbon mitigation sees, and concentration requirements, which is what climate sees? That has led to a number of projects. For example, the recently formed Carbon Human Emissions Project led by the European Commission, the NASA Carbon Monitoring System, and the formation of a constellation led by CEOS to be able to begin to look at and monitor the carbon cycle. But this then engenders the reverse question. How do you relate the concentrations that you see to the fluxes that you produce? That becomes within the purview of something that we call inverse modeling. And that question can be resolved in 3 parts. The first question is, what is it that you want to know? For example, this is using GeoSChem carbon flux estimates between 2011 and 2010 during the El Modoki El Nino. And the question is how well do you know already the Mexican fluxes, or perhaps Southeast Asia, or the Amazon? And you can represent that by a covariance matrix on those fluxes. That's step 1. Step 2 is, what can you observe? Let me get this going. This is column measurements from the OCO2 satellite covering, you can see large parts of the globe, at times going up in the high latitudes, but you'll see major components that are missing. For example, elements of Africa and in the Western Amazon. This has a big impact on what you and where you can resolve. That is step 2. Step 3. What is the relationship between what you can observe and what you want to know? And that is the role of transport. What you're looking at is a GCHP. This was a simulation run by Seb Eastham at C360, and you can see the very different transport patterns between what you're seeing in the tropics versus the extratropics, where the red values, for example, are positive CO2 anomalies relative to initial conditions. The blue is negative anomalies relative to those conditions, reflecting of uptake processes. And you can see the strong baroclinic activity and the transport from east to west, from west to east, in the transport patterns. That is a diffusive process, which in turn each changes our relationship between what we observe and what we want to know. So happens, that's the three components. If you take all those three together, you can form a matrix which represents the concepts of observing system, the transport and flux uncertainty, which includes both the transport here and its adjoint, a transpose, which in turn can be decomposed using a singular value decomposition, which gives you the primary patterns that you're sensitive to. This in turn can be used to calculate something called an averaging kernel, which is very familiar in the retrieval community and the inverse modeling community, which tells you what is the sensitivity of your estimate to the true state, true fluxes that you do not know. You can represent that by a low-order decomposition of this because it captures the primary patterns that you can measure and yet still represents the sensitivities at grid scale. So we're going to explore what this information can do by looking at an OSSE experiment. This is using OCO2 for the 2015 period. We had the large El Nino. This is the true fluxes for April 2015. This is a 40 var solution of that same case, but it's now done over each month from January to December of 2015. And you can see some places where you can resolve or where you can see information and places where you're not. And so we asked the question, how well can we do that? What kind of patterns can we control? The first one is, by decomposing this averaging kernel, you can calculate something called the degrees of freedom of signal. And for OCO2, that means there's 418 independent patterns that you can resolve based upon this analysis. But you might ask, okay, well, what about a particular location? How well can I resolve Paris? Or how well can I resolve Boston? Or in this case, how well can I resolve Congo? So we calculated this for the Congo region. And you can see that we calculate something called the impulse response, where we just change that specific location, we run it through the averaging kernel, and we can look at how the system responded entirely. That gives us a region of 15 by 15 degrees. So that's giving us now a sense of how well you can resolve. If you were to change 2 points next to each other, you would not be able to distinguish them. That's an important step forward. But you can not only resolve in space, you can also resolve in time. This is the impulse response, not for that same location, but for different parts of the year. So in August, you can do it quite well, as you can see here. But in March, you cannot. You cannot resolve very well the fluxes that occurred in March versus those in April. And that's because when you have changes in cloud cover, your ability to actually capture the concentrations takes time. Now your ability to distinguish them is much more difficult. And with that, I'll probably leave.
Kevin, I think so. We need really a very high accuracy flux estimate. So based on your own estimate, which one is the bottleneck, the certain measurement accuracy or the retrieval system?
So the analysis, the observing system, systematic errors in the observing system aren't getting captured in that analysis. My guess is that that will go up, but the transport is still probably going to be one of the dominant terms, particularly as a set of geostationary centers come into place.
Kevin, is your conclusion that the current satellite observing system cannot be used to verify national commitments?
No, I would not say that. I would say that the sensitivity to do that changes from location to location. In places like the tropics, where you're seeing fairly convective transport, I think we can begin to see the total flux changes with some degree of resolution. Yes, a continent scale. Certainly not resolving Luxembourg. But I think when you start talking about the regions such as North America, I think we're beginning to see those kinds of sensitivities.
Any other questions? Okay, well, now that's
So Kevin, could you comment on the accuracy needs for your transport simulation? For example, switching between a lat long grid to a cube sphere grid, how might that empower your inversion analysis?
So I think one of the biggest challenges that we have for something like these kinds of systems is the relationship between vertical and horizontal resolution and vertical and horizontal transport. So the real question is, when you start changing those grids, how are you going to change how air is moving up and then out? And I think that's one of the very difficult challenges. So the hope here is that not only can we better resolve the advective piece, but we can also resolve better the convective piece.
Okay, let's thank Kevin for clarifying that. And our last talk for this morning's session is by Lee Murray from the University of Rochester, who will talk about optimizing OH distributions using 14CO and metachloroform in the GSM adjunct.
Thank you, Dylan. So characterizing abundance and variability in OH is critical for atmospheric chemistry. And traditionally, this has been best achieved by looking at variations in the decay rate of methylchloroform in the atmosphere after it was banned. Once the residual emissions became much smaller than the chemical loss term, we had relatively good constraints on how OH varies in the atmosphere. However, those constraints weren't without uncertainties, including how you go from discrete station sites to global burdens, which can introduce uncertainty in the perceived OH variability. But most critically, the fact that we are beginning to approach methylchloroform detection limits in the atmosphere and therefore need to come up with useful alternatives. So one possible alternative is to go back to the very first proxy that was used to infer OH in the atmosphere, which is carbon-14 of carbon monoxide, which is produced by cosmic ray spallation in the polar UTLS before it is transported downward and equatorward in the atmosphere and oxidized by OH to CO2. There's a slight complication by the fact that the 14CO2 is assimilated by the biosphere and can be re-emitted into the atmosphere, but isotopic analysis suggests that the majority of 14CO present in the troposphere is from this primary production. So as long as we have good source characterization, this is a relatively simple budget, and we can infer OH variability. So the first step was to develop a forward 14CO model for geochem. So I created a cosmogenic source production regime that varies with pressure, Earth's magnetic field, and the solar cycle. This is basically just like the tagged CO version, but just 14CO. And for now, I have not yet implemented the secondary source. But even with just the primary source, the forward model shows quite a bit of skill in reproducing the historical variability seen in the last time that 14CO measurements were fairly trendy in the 90s. So we're capturing very well the solar cycle variability, the seasonal due to strat-tropic change, and then the meridional associated with the transport and photochemistry. So then we developed an adjoint of the 14CO model. I modified Kelly's N2O observation operator to work for my 14CO surface measurements, and then modified the assimilation machinery to optimize the global OH distribution as the state vector. So this is showing the adjoint sensitivities, zonal at 500 millibars in the surface, to biweekly sampling, hypothetical sampling at Mauna Loa. So basically you see, given as expected for a gas with a lifetime of a couple months, sensitivity between where you're doing the sampling and where it's being produced. So we can increase the sensitivity by having additional sampling, in this case at 7 global atmospheric watch sites that might theoretically host these measurements. And that increases global coverage, but we still see a hole in the tropics, since no 14CO really ever makes it across the ITCZ. And this is generally consistent with the already existing TM5 14CO adjoint conclusions from the mid-aughts. However, once the 14CO model was set up, it was trivial to create a methylchloroform adjoint. So if we do the same theoretical or hypothetical calculation, given the much longer lifetime of methylchloroform, and then also the fact that the reaction rate is extremely temperature sensitive, we see strong sensitivity to the tropics from methylchloroform. So we've begun to do preliminary assimilations of the data in order to learn about OH. So I'm going to share a few of the preliminary results in my remaining few minutes. First, I assimilated a decade of methylchloroform data, so from 99 through 2008. And it appears that our relatively ancient offline OH fields are dramatically, well, not dramatically, but strongly underestimated, particularly in the tropical free troposphere. Second, the temporal variability of the OH over this period from the 40-var method is consistent broadly with the earlier studies that have been done with various gases using single box or multi-box models, as shown in this plot from Alex Turner's 2017 paper. Lastly, my colleagues at Rochester began sampling 14CO again at Mauna Loa in a pilot study. It's not coincidental or uncoincidental, that's why I started exploring Mauna Loa. And when I assimilate these biweekly samplings in Mauna Loa and calculate what the OH corrections are, and then compare to the methylchloroform for the same period, we find the two independent methods to be consistent with one another, given the knowledge of the spatial and temporal distributions of the adjoint sensitivities. And all of this was funded for the purposes of model development in support of my colleagues who spent 6 weeks on Law Dome in Antarctica, drilling a lot of ice, melting it in the fields to bring back the 14C to Rochester to be analyzed. And then we will be performing OH inversions in order to use this proxy for OH variability since the pre-industrial, or I guess early pre-industrial to the present. But we're looking forward to doing a lot of applications now that this capability has been developed, including bringing in additional halocarbons and perhaps most interestingly, assimilating multiple species at once. So I'll just leave my summary up here and be happy to take any questions.
How well pinned down is the 14CO source in the US?
So I personally, I was floored when I saw this figure. So the high latitude sites are particularly sensitive to the source regime, whereas the tropics are not. And the fact that we are well able, and the production, the parameterization is based on theoretical calculations that we're capturing the interannual variability, especially with the solar cycle. I think it's strong evidence that we do have a lot of skill, but I'm planning on independently verifying this through a variety of other methods, including some balloon measurements that have been taken with 14CO profiles.
And so did you consider the different reaction coefficient for carbon CO, the 14CO because of the isotope fraction?
Yes.
How large is the difference, just curious?
I did not test I did not do that simulation yet.
So the OH, the uncertainty in this OH field in current years is about maybe 5%, 10% or so. So I wonder how will this approach, how much will this approach help reduce this uncertainty, especially given the large 20% emissions source from this biogenic sources, which we will understand to be quite uncertain because of our limited knowledge about the biological process.
So the 14CO measurements have always been designed to be as far from the secondary sources as possible. So in some ways that helps mitigate against those errors. But yes, I do have high hopes that we can at least correct the first order issues with the offline OH that we're using in GeoSChem. Notice it wasn't too bad in the mid-latitude, mostly a tropical problem. And this is something that I've seen before in the model when I was previously working with methylchloroform. Can you remind me of what part of your question was?
My question is that you say 25% from this carbon from biogenic.
Sorry, less than. So it could be like 1%. That was just the upper limit for what the secondary source has been estimated to be. But once we definitely will be implementing the secondary source and trying a wide range of possible amounts of secondary production.
You said you're going to go back to 1880. to do additional inversions. I'm just curious, how do you plan to do that with geoscale adjoint and some abundant land simulation?
Yes. Well, first we would just do it with modern meteorology, but then the goal would be to modify the ice cap framework to work and drive the adjoint fields.
Is there any reason to expect that the secondary source might change in terms of its contribution?
A huge reason, thanks to nuclear testing in the 50s, we are presently well above the natural radiocarbon abundances. And so that's my colleagues who do this in the ice core record, that's their main pain that they have to deal with. Since you had a huge spike of 14C in the 1950s that is slowly now passing through the entire biological reservoirs.
So your increase and decrease in OH happened over roughly the same timescale as the solar cycle. So how confidently, I mean, you're resolving the seasonal cycle here, but we don't have enough data to say whether we understand the 14CO source over the solar cycle. What do you think about that?
That's an interesting point. We do see it in the box models as well, so it's probably something that we would see, or sorry, that'd be an error that they're also experiencing. As you notice, I haven't shown or done any error characterization yet of the assimilation, but that would be something definitely to take a look at. I did quickly try to find if there was any large-scale climate, so the spatial temporal patterns of that in the optimization is primarily in the food troposphere over the oceans, but it's not a pattern that looks explicitly like ENSO.
What's the global mean OH burden that you're estimating from your inversion, say, an annual cycle? How does that compare to, say, Spivakowski et al.?
I have not yet calculated that number.
The reason I'm asking is that you're seeing an increase, I think, that's what you said. Right?
Yes.
But much of the CO inverse modeling work that's being done is arguing for a decrease in OH. So how do you reconcile the results with what we're seeing from the CO inversion analysis?
That the CO inversion analyses are potentially more sensitive to the northern mid-latitudes, given where the CO is and where the emissions are, whereas methylchloroform is biased towards the tropics. And therefore, it could be just a difference between the sensitivity of the inversion.
So you have to account for hot CO from nuclear industry and hot methane from nuclear industry?
So for the 14CH4 simulations that we're putting together on a different project, definitely for the 14CO budget, that's a relatively small fraction. But for the 14CH4 budget, that's a very large fraction. And we don't have good constraints on that.
Okay, let's thank Lee again. And now move on to the poster introduction session. Please, if you're presenting a poster in C1 through 12, please line up here on the left so that we can go through the poster introduction.
We're doing this.
I got it.
Yeah, if we have are we missing our first presenter?
I don't see Sajeev. Sajeev. Missing 8 and 1. We are missing number 1. Is Sajeev?
Actually, I haven't seen Sajeev. I had not seen him.
I saw him on Monday, but okay. All right.
Go ahead and do it, though.
We'll move on to.
Hi, I'm Doug Finch from University of Edinburgh, working with Paul Palmer, and we're doing a preliminary study looking at the methane hiatus, and if we can discover a bit more insight into what happened there, we're using long-term observations of ethane and propane and the ratio between the two. We're developing a tagged ethane and propane model based on the tagged CO model, and then from that we can look at source change over the past couple of decades and see if we can get an insight into what's happening. So if you'd like to come along, I'm number one, not two.
Hi, I'm Alice. I'm a first year PhD student at the University of Edinburgh. I'm looking at modelling clumped isotopes of methane in geochem. Clumped isotopes are where you get more than one isotopic replacement within the chemical structure. And despite their really low concentrations, these could prove to provide a powerful constraint when estimating methane fluxes. So if you'd be interested, come and chat to me this evening.
Hi, I'm Yingjian Shi from University of Rochester. I'm now working with the Murray on a methane simulation project. We are trying to build up a working isotope log methane simulation. We are trying to include both stable isotopes like carbon-13 and deuterium, but also radiocarbon. I'm now only working on the stable ones. So we are trying to modification the emission part with isotopic signatures and also try to optimize the chemical reaction part with kinetic isotope effect. So if anyone is interested, I'm at C4. Thank you.
I'm Zichong Chen from Johns Hopkins. The OCU2 satellite has provided a novel opportunity to estimate the global surface CO2 flux. We are estimating the global CO2 flux by coupling the geochem adjoint of 40 var with a geostatistical inverse model. One really unique aspect of the geostatistical approach is that we do not actually using any bottom-up flux model or emission inventory in the inversion. Instead, we assimilate a wide range of environmental driver datasets like meteorological forcing, vegetation indices, and land cover datasets. Using this approach, we can not only estimate the CO2 flux, but also can figure out, analyze what environmental drivers datasets are like actually driving the variability in the flux over the globe.
Hi, I'm Kelly Graham from Florida State. I'm doing some CO2 inversion work for surface fluxes in the Arctic Ocean. So if you're interested in inversion work or in the Arctic carbon cycle, come talk to me in my poster C6.
Hi, this is Nozrul Islam from UNBC. First, we use ghosted data in a simple mass balance method to estimate oil and gas methane emission in Western Canada. We also performed geochem simulation and found very consistent profile information compared to the collocated to aircraft station. But the emission based on GC simulated products, we found emission based on this product is twofold lower than the satellite-based emission. We also investigate the tropomy data to investigate the capacity for our future work. So thank you very much.
So this is not mine.
Oh, we're missing our.
This is number 8.
Okay.
Okay, so I'm Loretta Mickley. And in 2009, under President Obama, the EPA issued the endangerment finding, allowing it to regulate greenhouse gases, CO2. Now we have a different president, and we've gathered together new scientific evidence supporting the endangerment finding, including work done here on the climate penalty on air quality, on ozone PM2.5, wildfire dust. I'm showing some interesting results about dust. This work was done by Lu Shen, Pelagia Kolwizet, with help from Amos Tai and Melissa Solprizio. Thanks.
Hi, I'm Hairu Tang from Peking University. Right now, CDS is not a candidate of anthropogenic emission choices in methane simulation of geochem, and the default Edgar emission differs in the total and trend with CDS over China. So we simulate methane with these emissions and evaluate their performances by comparing the interannual variability and trend with different observation data. So if you are interested, please come to my poster and see.
Hello, everyone. My name is Xing Yu from the University of Minnesota. We have some new aircraft measurement to constrain methane sources in the U.S. Midwest. What is shown here are flat tracks colored by methane observation. We optimize the regional flux based on those aircraft measurements in the geochem adjoint. And we also did point source quantifications along the flight. Thank you. If you are interested, please welcome to my poster.
Hello, my name is Hannah Nesser. I work with Danielle Jacob. Tropomi now provides daily global retrievals of methane mixing ratios at 7 by 7 kilometer squared resolution. These observations allow us to constrain methane emissions at high resolution. However, inversions that constrain emissions and characterize error are computationally expensive. If you are interested in talking with me about how to construct Jacobians for high resolution analytic inversions, please come talk to me at C12. Thank you.
Okay, please join me in thanking all of the speakers and the poster presenters. And we'll take a break now and start again at 10:40.
Thank you, Dylan.
All the talks are on the flash drive except for missing Shinta's talk. Where did it just go?
Okay. My name is Bojan from National Institute of Aerospace. I think we have heard a lot of talks about model development and about emission chemistry, scavenging schemes. Today, I really want to bring up a real science question to see if our model can really work as an integrity to solve things we see in the observation. So the science question I'm trying to see is the Asian troposphere aerosol layer, which is also called ATEL. And the idea is try to see if the current model we are using can help us understand the composition, changes, sources of the ATEL aerosol layer. And also want to thank all collaborators from NIA and NASA Longley for their input to this presentation. The Asian troposphere aerosol layer is formed through the deep convection in the Asian summer monsoon. And the story behind that is once all the aerosol lifted in the UTIS is kind of trapped by the anticyclone layer, and the air exchange between the ATEL and the surrounding air is kind of slow. So the aerosol accumulated like a flask of aerosol layer between 15 to 18 kilometers. And this is confirmed by the long-term satellite data from CLIPSO and SIGURS. Not only the transport in the summer monsoon is important, but also the release factor of the aerosol and the formation of ice clouds in the ATEL region important to the local climate. So we have a few research after going at NASA Longley and NIA. We had the Bloom campaign in 2017, and Jean-Paul Vernier led the investigation of aerosol composition, and we found nitrate was the dominant aerosol component in both Bloom launches. And our mate Candice also led the investigation of the measurement of ice cloud optical properties in ATEL. This is work, a manuscript led by Duncan Fairley from NASA Longley as well. And in this work, we used geoscam to investigate the source and composition of ATEL. We found by using the physical SO2 scavenging in the convective object in the model, we kind of underestimate the ATEL, which shown by the standard geoscam output here. And with this switch to a more realistic Henry's law-based scavenging coefficient, we had a much better result in the model. And another message from this manuscript is that about 6% of sulfate in ATEL is from the India and the China emissions. This is kind of conflict with the previous study about sulfate simulation, and the idea behind this is that in different model can we really simulate the sulfate lifetime and rights in the UTLS region. Another work which I have been working on for a while is inspired by this long-term observation of CLIPSO aerosol backscatter ratio from 2006 to 2016. So the backscatter ratio of aerosol is the backscatter of aerosol divided by the total backscatter of aerosol and molecular. And if you compare the left column and the right column, you can see a clear reduction of this ATEL region reflected by the area of the backscatter ratio. And also, if you compare some of the adjacent years, see here, and 2014, 2015, you see that a big change between the adjacent years. So we want to see what the model can tell us what's happening there. So we set up a two-step plan. We are using existing long-term high-resolution model product MERA2 GMI to identify some anomalies in the ATEL region. So what may pop up to us to study. And the second step, the idea is to use geoscam to focus on a couple of years and play with the emission switches or the regional mass to understand the contributing factor to the idea of ATEL. So here I'm showing some preliminary results from the modeling part. So here I'm showing the same aerosol backscatter ratio at the level suggested by the satellite data from MERA-2 GMI. It was calculated based on the aerosol extinction and LiDAR ratio from the front model. So here we don't see a very clear change, the reduction trend in the aerial detail. So it's not a big surprise. But because there's emission changes, there's updates of chemistry schemes. So let's take a close of some simple questions, a few years to see what the model can give us. So we choose 2 years to take a close look, 2014, 2015. The reasons are it looks very different in the satellite image. And for 2015, it was an linear year, and we hope to find some transport different there. So here's are the close look of the 2 years, the same satellite image, the same model result. Now I'm doing a little bit different, just change the color bar a little bit to see what's the details in this saturated area. So it looks like to me that in the model, in the MERA-2 GMI, it's more stronger in the 2014 with contrast with the satellite. But when we sample at a little bit lower in the upper troposphere, the 2015, it's turned over and it's matches much better with satellite data. The story behind that was in the model, the nitrate and sulfate, which are the two major components in the model, kind of located at different layers. So when we sampled at the layers suggested by the satellite, we only capture sulfate, but we only touch a little bit on nitrate. So from this cross-section of here, you can see if you go actually deeper in 25, it will be much stronger, and you will get a 10 over here. So that's MERA-2 GMI, and this is GeoScan, but with a coarse resolution 2 by 2.5. You can see the similar contrast here, but you can see the stronger signal from the cross-section. So when we have a conflict between the satellite and the model, we really blame the model. But the point I want to make here is that when we look at this information, there's a lot behind that except the transport and scavenging and chemistry. So we really want to look into that to see what's happening in the model. Thank you very much.
Very good question. Oh.
Could this aerosol go up into the lowermost stratosphere and start depleting ozone? I hear a lot about this over North America from my colleague Jim Anderson, but I'm wondering if that could happen over South Asia as well.
Competing ozone?
Well, you know, create some PSC chemistry as you get into the...
Yes. We actually found a depletion of ozone in the ATL region. Yes.
Thank you again. Our next speaker is Emma Nolan from NASA, and she's going to be telling us about very high-resolution forecasts.
Thank you. Thank you, everyone, for this amazing opportunity to share with you our new GMAO product. There's a small team of us at NASA Goddard who have been working together to develop and evaluate this new composition forecast using the GEOS model. The GEOS model is an Earth system model that's designed mainly to advance the use of satellite data products. We have two main branches, forecasting and reanalysis, which you're all pretty familiar with by now. GEOS FP standing for forward processing, is our flagship numerical weather prediction model. And as Andrea mentioned earlier this week, this model is actually updated as frequently as twice a year. So if you're running GeoScam with FP, please keep in mind these updates. MERA-2 is a reanalysis product. And so this takes a frozen version of the FP model from a few years ago, and we reanalyze the observations since 1980 in order to have a consistent data set. One that you're probably not aware of is GEOS FPIT, Forward Processing for Instrument Teams. This also uses a frozen model, which is very similar to MERIT-2, but it has slight differences in the observing system in order to work with our instrument teams. And we're using this product in order to drive our GeoCF, our composition forecast. And so for over the last year, we've actually run GEOS with GeosChem in order to simulate our weather and our chemistry on the same resolution. And we're actually using the same GeosChem version that you are, version 12. And so this way we can actually benefit from all of the model development that this community is making. Keep in mind, though, that there are some differences in our emissions because we are running this in near real time. So once a day, we launch a 5-day forecast. It starts when the FPIT finishes its 12Z forecast, which right now with daylight savings means that it starts at about 3 o'clock. So first, we run a 1-day replay. So we rerun the past day's meteorology with GeosChem in order to get the best initial conditions for our 5-day forecast. We're running this at a high resolution C360, so on the cube sphere. This is about 1/4 degree, 25 by 25 kilometers. And we have very high temporal frequency. So we have some surface diagnostics at 15 minutes, but most of our output is saved at the hourly resolution, either time average or instantaneous. And we're releasing data since the beginning of January of last year. Do keep in mind that currently we do not have any direct data assimilation of constituents in the GeoCF, but we do have impact from satellite information, such as GoCart, which is also run in the CF system, and this is constrained by aerosol optical depth from satellite, and these GoCart aerosols actually feed back on the meteorology in the system. We also use the near real-time QFED product, so this is one of the differences that I mentioned before. So here's an animation which is focusing on this time period in 2017, which is one of the peak fire seasons over India. And on the left-hand side, you can see PM 2.5 simulated from the GeoCF. And on the bottom is a time series showing each day's individual forecast starting in red. And as it goes out into the 5-day forecast, the color kind of fades out into a yellow. See if I can play that again. And you can see that we actually had good agreement. So sorry, I moved on. So this is an animation Stephen was trying to show you earlier this week, so I know you've been patiently waiting for it. So this is actually showing NO2 over Europe, and you can actually see how those scale factors that we applied for diurnal as well as day of the week actually capture nicely that variation in NO2 over Zurich. You can see that weekday to weekend. Another way that we're kind of starting to introduce this idea of data assimilation into the CF system is that we're actually relaxing our stratospheric ozone to the GEOS FP assimilated ozone in order to get the best product that we can there. And hopefully you met Pam Wales yesterday at her poster. She started with us during the January shutdown. And in the past few months, she's done a great job starting to evaluate the stratospheric composition. And so this is a figure from her showing bromine and chlorine content using some long C48 runs from Eric Fleming at NASA Goddard. The solid lines are using GeosChem. And the dashed line is using GMI. And you can see that the GeosChem is capturing quite nicely the bromine and the chlorine content compared to aircraft observations in the circles for the tropical tropopause area. And if you can see, I know it's probably quite hard, but at the very end of the time series, there are these crosses, and that's 1 day from last week of the GeoCF. And we can see that for these long-lived species, we're capturing quite well the chlorine and bromine content. So keep an eye on our new website, fluid.nccs.nasa.gov/CF for composition forecast. Here you can find right now maps of our recent forecasts, and we're working with the developers of Fluid to get data as well as other diagnostics online to be able to share with you. So you can see here, I took this snapshot from earlier this week, the forecast for yesterday's high ozone events, where actually if you checked air now, you would see that there was moderate ozone AQI in quite a bit of this area here where we forecasted higher ozone. And so with that, I'll show the other animation that Stephen was trying to show, and I'll happily take any questions.
So, Emma, the Chorus AQ and the upcoming Fire AQ-AX is a great opportunity to evaluate the performance of this system. We have both satellite measurements and surface measurements. What are the steps towards beginning to assess the quality of the forecast?
Yeah, so we're actually working with our first NASA mission this week, which is SCOPE. And so hopefully, as we go forward, we can work more with missions, especially NASA missions, in order to share information and support them in near real time. Does that answer your question, Kevin?
Well, that supports giving them information to them. We want to know is what's the actual performance if you're comparing against AIRS ozone, TESS ozone, CRIS ozone, CO, et cetera. What is it looking like on global scales and regional scales? So right now, those look beautiful, but we want to know what the actual performance is.
Yes, yes. And I should give a plug then for Christoph Keller's paper that he's working on, which will go into full evaluation of the product. And hopefully, as I showed at the very beginning, there's a small team of us. And so hopefully getting this data out there, we can definitely work together to evaluate. Thank you.
I just had a question. I don't know a lot about go-kart. I'm a little bit more about how that works with geochem and sort of go-kart AOD.
Fancy you asked. So yeah, we are running go-kart and geochem simultaneously. So the way Geos model works is that we can have different modules running together at the same time. And so right now they are separate. In hopes in the future that we can actually get the best of both worlds, because Geochem has the SOAs and the reactive gas chemistry, which go-kart does not. They both have that bulk aerosol scheme, so we're hoping to be able to work together between the two. Thanks. If anyone would like a Meritu sticker or their own C6 cube, do let me know.
Next speaker is Jin Tai Lin from PKU. He's going to tell us about recent progress in studying global air pollution.
Hey, thank you very much. So my group has been working on this problem of globalizing air pollution over the past few years. And so, and this globalizing air pollution is because of the coupling between atmospheric transport and economic trade. And so we do this, we study this problem by integrating satellite remote sensing, high resolution modeling, as well as emission economics modeling. But today I'm only going to focus on the satellite and modeling part of our study. Okay, so first I want to, today I'm basically want to introduce various kinds of data set and tools that we are developing so that you guys can use if you're interested. So the first one would be our Pominol NO2 product covering China and its nearby regions. As you can see, this is the monthly animation of NO2 over China. And below, you can see very detailed spatial and temporal variation of NO2. And what's special in this algorithm is that we are the first and probably still the only one in the world to explicitly consider the effect of aerosol optics. Also, we also have this cloud retrieval, which has these consistent, how can I say, ancillary parameters with NO2 retrieval. And we have a lot of user bases right now. We have users from more than 50 institutes from 4 continents. Now we kind of develop, apply our product to Trapomi to have this new product. I can see compared to the official KNMI product, we show the urban signal much better than And if you compare with max loss measurement, you can see again our comparison is much better than the official product. So again, we are going to release this product in like within half a year. So if you're interested, just contact us. We can also combine this satellite high resolution satellite measurement with our flat inverse modeling tool to really capture, really invert NOx emissions at a very, very high resolution, in this case, 5 kilometer resolution. I only show you here the example over a Shanghai area from 2012 to 2016 in summer. You can see this is the satellite NO2 VCD, and this is our retrieval, and this is the make emission inventory everybody use over China. You can see there's huge differences, of course, and we show a very strong localized signal as compared to this make inventory. And over the ocean, we have a lot of emissions. That's because of this strong shipping, which is completely missing from the inventory. Okay, now let's move on to the modeling part of our study. Previously, we developed this two-way coupled simulation system based on our own PKU coupler to combine low-resolution global geoscam model with its high-resolution nested simulations. And you can see that by comparing to the low-resolution global model, our two-way modeling actually reduced the tropospheric oxidative capacity by a very significant amount. So we reduce OH, reduce ozone, increase CO, increase the lifetime of methane and MCF, etc., etc. So basically, so a lot of users here worry about how to not break the model by implementing various things. And in our case, we never break model in any way. We're actually improving the model towards the observations from both for OH, ozone, and CO. Okay. We also have this new development of implementing aromatic chemistry in geoscam. Now, if you use geoscam, you will see that aromatics only affects OH reacts aromatics in the model to produce SOA, but there's the whole chain of chemistry that affects the gases is missing from the current simulation, so which is wrong. So we basically just copy this Spark 11 chemical mechanism into the model, and this is the simulated changes with and without aromatics. And you can see that it's a very strong changes in many regions. Also, you can see that in this study, we only use these very old emissions for aromatics. So if you update this new emission, update the emissions to newer years, you will see a much stronger impact. Okay. So we also use this modeling to calculate, for example, the global the impact of global anthropogenic emissions from China on Chinese ozone. As you can see, that this red curve shows the vertical distribution of anthropogenic ozone due to Chinese own emission. And you can see only 50% in the lower troposphere to about only 15% in the upper troposphere, and the rest of it is actually of foreign contribution at this point. Okay, and last, I want to show you guys that now we have a lot of observations in spatial and temporal space. We also have modeling in spatial and temporal space, and the question is that how could we best or do our best effort to squeeze to quantify the different modes of variability from this model or measurements. So for this purpose, we actually developed this EOF and EMD tool. So basically, we use this EOF to separate this spatial and temporal mode, and we also use EMD to kind of diagnose the different temporal modes in each PC. And this is the end result applied to the this fall winter 2014 over East China for NO2, and this is the measure of NO2 result, and this is for the result for geoscam simulation. As you can see that there's very strong diurnal signal as well as the day-to-day signal in the observation, which is much missed are missing in the model simulation for this particular set of model. So I think I'll stop here, and thank you very much for your attention, and a small advertisement for both our faculty positions as well as our postdoc positions. Okay, thank you.
Is two-way nesting going to be part of the adaptive nested grid that's a new development in GeoSCAM? And if not, is it feasible to implement it?
Well, in this case, there's no need to do this adaptive thing. I mean, just turn it on, turn it on or off. But for this adaptive thing, I think you are talking about GCHP mostly, which is.
Sorry, I'm probably using the term. Yeah. Flex grid.
Okay. Okay. Yeah. Of course. Yeah. It will work seamlessly with this flex grid implementation done by Jiawei Zhuang. He actually initiated this idea when he worked at PKU. Okay.
So you showed these large changes in OH with the two-way nested grids. Yep. And then on top of that, the aromatics. So is that changes because of aromatics, or on top of those changes because of the nested grid?
They're actually kind of separate. So kind of separate development. But you can say on top of it. Yeah.
And the change is still consistent with
I think so, yeah. Because the change due to the two-way coupling is much larger in the troposphere than the change due to aromatics.
Can you tell us why, what's the main challenge with the explicit aerosol collection, and why haven't NASA or KNMI, why aren't they doing it?
Well, there's a lot of reasons. One of resource-related reasons, manpower, and many other things. But I wouldn't speak for them. That's my only guess. But they're actually considering, based on our previous work, they actually considering to explicitly treat aerosols in a slightly different way, though. Yeah.
Can you just talk a little bit more about the main benefit of two-way coupling is and why that gets you better results?
So basically, two-way coupling reduce the oxidative capacity in the whole troposphere. So, and the reason being that when you do the coupling, you actually first use the nested model to capture this smaller scale, chemistry. For example, urban rural or urban remote area signals. And so actually, when you look at your nested one-way nested simulation, you always see that on domain average, you have lower OH and lower ozone as compared to the global simulation. It's just that when you don't do the two-way coupling, you just kind of get rid of all these signals because the nested model is being replaced. It's being driven by this lateral boundary condition from the global modeling.
Again. Our next speaker is Betty Croft from Dalhousie University. She's going to be telling us about applying GeoSCAM Thomas to understand Arctic marine secondary aerosol contributions.
Okay, thanks. So let's think together for the next few minutes about the Arctic, which we know is a region that's undergoing rapid change. So we've been using the GeoSCAM model to interpret measurements that can help us learn about how aerosol particles form and grow in the summertime Arctic. And although this talk is focused on the Arctic, it has relevance for other marine regions as well. So just to motivate this, let's look together for a few minutes at some measurements from the summer of 2016, taken from a ship track through the Canadian Arctic archipelago, and also from ongoing measurements at Alert and Eureka. And typical of the Arctic summer, if we look at the time series of the total number concentration of aerosol particles, we can see that there are these fairly frequent spikes, which are indicative of times when aerosol particles are forming and growing. And as well, if we look at a summertime median size distribution, down on the bottom here, the number of aerosols as a function of size, we can see that the majority of these aerosols have diameters between about 10 and 100 nanometers. And most importantly, we now have a lot of observations from the Arctic of these growth events. So these so-called banana curves, where over the course of several hours, the aerosol particles are growing by some tens of nanometers towards sizes that can be relevant for climate. So if you care about climate, you might be interested to ask the question, what processes are growing these aerosol particles to climate relevant sizes in the summertime Arctic, sizes of around 50 to 100 nanometers? To think about this, we can use a size resolved version of the GeoSchem model with aerosol microphysics included. So with this aerosol microphysics, we can represent the processes by which the aerosols are growing by condensation of vapors and keep track of the number and mass of aerosols in a set of size sections. So we use the Thomas version here. So if we look at our simulation with the model shown in orange here relative to the measurements shown in black, we have quite a few aerosol particles that are about 20 to 30 nanometers. However, on all three measurement platforms, we really underestimate the number of aerosol particles with diameters larger than about 30 nanometers. So we have this issue of missing growth. So to think about this and put it in context, let's remind ourselves that in the summertime Arctic, the boundary layer is frequently very cloudy. There's drizzle, which efficiently cleans the atmosphere and maintains it in a state that, as Steve reminded us at the beginning of the morning, is not pristine, but it's certainly relatively more clean than at lower latitudes. And also it's a region that's strongly influenced by the biological activity that's occurring in the oceans and along the coastlines. So these simulations do include updates with more vigorous wet removal to account for the effects of drizzle in the boundary layer, and they include ammonia from seabird colonies and tundra, and some scaling of the nucleation rate to account for vapors that could nucleate new particles that could be missing from our simulations. But still we have this problem with not enough growth. So we can turn to the recent measurements to give us some indications of where to go next. And measurements suggest a role for Arctic marine secondary organic aerosols. Sort of moving from the left to the right here, we now have measurements from the sea that indicate that the sea surface microlayer is a source of SOA precursors. We have measurements that indicate a marine source for these condensing organics. As the more time the air spends over the open water, the greater the organic contribution becomes. And very importantly, on the far right here, we now have measurements from growth events where we can see that the composition of the growing aerosols, these 50 to 100 nanometer particles, is really dominated by organics. So motivated by this, we introduced into the GeoSchem model a flux of condensable VOCs from the ice-free seawater of the Arctic. And we looked at how much we would need in the simple SOA scheme to improve our simulations to a satisfactory match with the measurements. And it was about 500 micrograms per meter squared per day of a VOC flux. And then as we expect, we can see the red curve now shows a closer agreement with the measurements. And if we revisit on the bottom, on the far left, this banana curve that we have from observations, just as an example, we can see without these condensing organics forming the Arctic marine secondary organic aerosol, we don't really have the banana plots in the simulations. But if we look at the two curves, or the two plots on the bottom right, we can see that with this additional source of condensing organic vapors from the oceans, we now have these banana plots of growth. And there is a sensitivity that we find in the simulations to the assumed volatility of the condensing organics. And measurements indicate that the condensing organics are surprisingly more semi-volatile than what you find at lower latitudes. So we can kind of step back and then take an inventory of our simulation and look at the size resolved mass contributions. And we can see that between 10 and 100 nanometers, these aerosols in the simulation are predominantly secondary aerosols. And these are the aerosols that are growing to be big enough to influence climate. So we find a really strong role for the Arctic marine secondary organic aerosol coming from the VOCs. And these aerosols are expected to have a climate relevant effect. On the smaller side, there's a stronger role for the biogenic sulfate, which is in keeping with measurements of around 10 nanometer particles growing more vigorously by the more non-volatile organics. So we can look at a geographic plot of the total number of aerosols with diameters larger than 50 nanometers, and you can see it's quite clean in the Arctic, but the Arctic marine secondary organic aerosol, or the AMSOA, makes a strong contribution to this number of aerosols that's climate relevant. And here we're just looking at the cloud albedo indirect effect. So these aerosols can act as seeds for the formation of cloud droplets, and that will make the clouds more reflective, causing a cooling effect that we estimate here to be significant. So just to wrap up, we find there is really strong biogenic influences on the summertime Arctic, and we have now measurements and modeling that offers support for climate relevant role for Arctic marine secondary organic aerosol. We've had a lot of really great talks about our progress moving forward to understand organics. And I think I would just want to add to that, that we still really don't understand very well the nature and the fluxes of the VOCs that can form SOA in the Arctic and also in other marine regions. And so this is an area that really needs, I think, to be looked into in the future. Thanks for your attention.
So I saw that you said that you have a 100 times increase in nucleation rate to account for missing volatiles. But we've also been another source of volatiles directly to the model.
Yeah.
Is this the cause of, we're seeing still that you now have like a large overestimate in the nucleation mode. Is this a result of sort of double counting, or is that something else?
Okay, so the scaling of the nucleation rate is kind of representing for those extremely low volatile organic compounds that can form those nascent clusters. And that's introduced, but it's not going to be contributing really to the growth and the mass that we see.
I guess then my question is, do you have any thoughts on why it is it seems that you do have now a large overestimate in the nucleation mode, especially on that first plot, whereas the rest of your distribution is great?
Yeah, I mean, I think if you look at this presentation, you realize like it's quite broad brush, everything we're doing. And so I really hope that it motivates people to get out and understand like what's the source of these vapors, what's the nature of these vapors, so that we can treat things a little bit better than just, scale it by a fixed factor or have a fixed VOC flux, from all of the water when it should really depend on, other factors. So I think it motivates the need for getting more understanding so that we can refine the parameterizations.
Thanks.
Yeah.
I'm just wondering, I mean, you sort of touched on it in your last bullet and in your last comment. Do you have any hypotheses or ideas about what the source of these VOCs are, what they depend on, and whether you'd expect them to operate in, say, the Southern Ocean or other regions outside of here?
Yeah, I'm really interested in that question about the Southern Oceans now. But John Abbott's group at the University of Toronto has been the measurement group that's really been working forward with a lot of these measurements. And what they're telling me from the measurement perspective is it's not typical biogenic SOA. It has a different character. They're talking about fatty acid type SOA precursors. And, so I think we really need to do work to understand it better. And yeah, I'm interested in other marine areas now too.
Kind of along the same line, do we know anything about the solubility or hydrophobicity of these organic components that presumably come from a microlayer that is somewhat hydrophobic, but is apparently contributing to CCN?
Yeah, that's a great question, and it's definitely an open area of research. I mean, we know that there can be some insolubility to these inorganics for sure. But it's not really well understood. And so I hope people get motivated and try to work to understand that more. It's a great question.
Our next speaker is Shilin Wu from Michigan Tech. He's going to be talking about the temporal resolution of transport.
Hello, good morning. I guess I'm not good at coming up with a title, but what I'm trying to show you today is, I think, a kind of a surprising discovery that we found that in certain cases, when you have very high temporal resolution, it does not lead to the good results. Actually, it could cause some trouble in the model simulation. Two of my former students have contributed to this work at a different time during their PhD. So I guess from there you could get an idea how long we have worked on this. Indeed, I first reported this a few years ago IGC9. So basically, so that we were looking at some data from the Arctic. And so we noticed a very surprising feature regarding the NOx. So we know Arctic is the Greenland Summit Station, pretty remote area. And we see that so normally you would have very low concentration for the NOx concentration there. But when we run the geochem simulation, we find that every winter you would have some very high episodes for NOx. Okay? So we're talking about 50, 60, or up to 100 times higher than typical NOx concentration there. We tried to, but these high specs never show up in measurements. That's a puzzle. So which is contrary to what we normally see that. Because as you know that we normally see the model would have trouble producing the peaks, right? But now we are seeing that many of these peaks in model but never show up in measurements. So we have tried everything we could, think of to figure out this. We changed the resolution. This was using 4x5. We changed it to 2x2.5, still the same thing. We changed the meteorology, from GEOS 4, GEOS 5, different meteorology, always there. We changed the chemistry, doesn't matter. So we changed the emissions. Okay, so we turned off the emissions one by one, anthropogenic emissions, lighting in soil, different regions. Finally, we were able to see that these specs were associated with anthropogenic emissions from Europe. But that's all we can see that. We still couldn't see what's causing that. So finally, we essentially give up on this. But we just published the paper saying that we see some large specs, but we don't know why. So I'm glad that that paper went through so that. But so it's not long ago. Started thinking about one thing we have not played with. That's the transport, the advection. So we're thinking so that if the numerical diffusion can play a role here. So we did some very simple simulation by just changing the transport time step. 30 minutes, 60 minutes, until so that 6 hours, which is crazy, right? But interestingly, we found that the spikes will disappear if you have a time step more than 1 hour. Okay, I mean that's pretty long, right? We know we always want to push for a shorter time step, 30 minutes, 20 minutes, if you can afford it, or even higher. But we found that this you can only remove these specs when you have very long time steps. And I think this is due to the numerical diffusion associated with advection. So if we have air parcels and we at some place, and so this will get transported, right? And so because we are dealing with different grades, so that so at time t, and you have it located in one grid box, and the next time step you will get transported. Okay, and in reality we know that the wind speed is not that fast. We're talking about several meters per second. But for this in the model, okay, so next time step you are guaranteed to have some effects from this grid box to that one. Okay, so that we call that the numerical diffusion. And also you think about magnitude. So how fast this air particle getting propagated is basically measured by delta x. You know, that we're looking at several hundreds of kilometers divided by delta t time step. So this is you always you're almost guaranteed to have a value that's much larger than the real wind speed. So you always have this artificial diffusion. And if you have a shorter time step, you would have more of this diffusion. And so this is particularly important for the remote areas where you would have typically the very low background concentration. Okay? So if you are wondering so that then what should I be concerned about this? I would say that probably if you are looking at mid latitude, probably not that a big concern because you have very high, much higher background concentration there. And we know that so if you look at the wiki, there's a recommendation for like 30 minutes, 20 minutes, the transport step. But if you are looking at remote areas and or if you see some weird things you couldn't figure out due to other process, probably you need to double check on the transport. I think that's all I want to see.
I'm very interested, but I don't understand the argument here. So basically, when you increase decrease the time step, so you say there's artificial diffusion being enlarged.
Yes.
But if artificial diffusion being enlarged, then you kind of have a stronger diffusion. So you wouldn't see a spike.
No, just because you have, you can think of this as, I think you can think of this as when you have a shorter time step, you are getting more of this artificial transport. It's faster. This air particle would be propagating faster, than the real wind. I mean, it's always getting transported faster. But if you like in the same amount of time, you would get more of this, basically more. Again, so basically each time step, so let's say from Europe to Arctic, and you normally take like 10 hours. If you have a time step so that you reduce time step, you would reduce the time for this air particle to reaching Arctic. If you reduce the time step by half, you essentially reduce the time needed for the air particle to travel there artificially again.
As the chair, he's jumping to ask a question. Are we concerned about violating the CFL criteria? So with taking on-time steps, again, I'm having trouble with the kind of my typical thinking of advection stability.
Well, we go to semi-Lagrangian, run the CFL variant, and
yeah, that latitude the cell's only 100% kilometers as well.
Yeah, you're probably going semi-Lagrangian all the time.
Yeah, but so long as you use the semi-Lagrangian, you would have this diffusion.
Well, but the advection scheme switches to semi-Lagrangian when the Courant number is greater than 1.
Oh, okay. Oh, yeah. Actually, point out we're using the old version of GeoScam. So since we started like 10 years ago to this version 9, I think that
We've always used some
There's more discussion about this, clearly.
Yeah, just the first, I mean, if you're looking for artificial diffusion then, and you're saying that your spike is due to numerical diffusion, was this spikes made over a large number of cells?
Made with large.
Right. If it was the result of numerical diffusion, it should be a very large, in extent, peak. Did you observe that, or was it isolated to a specific location?
Oh, we only looked at a specific location. That's where we have the data. But that's a good point. We have not looked at it. We could look at other places. Yeah. But I think it's pretty clear so that we only change the time step that will solve the problem. And that's the only way we find we could be.
Transport working group is going to discuss
is that it's European in origin because in winter, pollution from Europe is the only pollution that's making it into the Arctic. So one question is, in the Arctic, are you seeing anomalous vertical transport because of the fact that you're in this region, right over the pole, that is lifting the European signal up, so that you're picking up in the free troposphere in Greenland? Right? It'd be interesting to compare what you're seeing with what we might see in the cube sphere grid, where we're going to better resolve the Arctic transport. So it might be, you personally might want to look at higher altitudes and across the Arctic to see if you're seeing higher European NOx as a result of anomalous vertical lifting, which you're then picking up again.
Okay.
All right.
Yeah.
This is really interesting. I think there's a lot of discussion that we can continue to have on this topic. Thank you again. Our next speaker is Kazu Miyazaki. I'm sure he's going to tell us about assimilating all the things.
Not everything. Thank you, David. So I'm Kazu Miyazaki from JPL. So I'm going to introduce the new GeoScan ensemble Kalman filter data assimilation system. And I'll talk about multi-model, multi-constraint chemical data assimilation framework named the MomoChem system. Okay, so there are so many factors affecting the performance of data assimilation, as shown by these figures, including the forecast model, observation, and the assimilation scheme. Then because of the difficulties in implementing the common data assimilation scheme into different models, especially using the variational techniques, the impact of forecast model on the tropospheric chemistry data assimilation has not been clearly demonstrated in the past studies. So in this study, we use the common ensemble Kalman filter data assimilation framework and the multiple models to investigate the importance of forecast model performance on tropospheric chemistry data assimilation analysis. And we provide the multi-model integrated data assimilation analysis using this framework. So the common data assimilation framework has been implemented into 4 models, including the GeoScan and the 3 Japanese models. The GeoScan model used in this study is the version 35 adjoint, which corresponds to the version 9 for the model, so which makes us possible to make the intercomparison study between the 4D VER and the ENKF in the another study. Then the Japanese models used are the IGC9 chaser, which was used to make our first chemical analysis calculation, the TCR1. Then the second one is MIROC-Chem, which has more detailed chemistry both for the troposphere and the stratosphere. And its high-resolution version, MIROC-Chem-H, which was recently used for making the second version of tropospheric chemistry analysis. Then as shown by this figure, that in the multi-constraint chemical data assimilation framework, the assimilation of the individual measurement provides information on the different aspects of tropospheric chemistry system. Then the concentration and the emission sources of the various species are simultaneously optimized using the ensemble Kalman filter data assimilation to provide the comprehensive constraints on the entire tropospheric chemistry system. Then this figure compares the global ozone distribution between the model simulation and data assimilation analysis and test measurement for the whole modeling system. So the most of the model biases are removed by data assimilation, as shown by these figures. Then the multi-model spread of ozone in the middle troposphere is reduced from the 5 to 10 ppb to less than 3 ppb by data assimilation. So this suggests that the data assimilation provides the highly consistent analysis fields of ozone, which is less dependent on the performance of individual models. Then we also analyze the data assimilation statistics, such as analysis increment and analysis uncertainty. So this figure compares the annual mean analysis increment, which is the adjustment by data assimilation. So that analysis increment structures are largely different among the models. And this information could be used to suggest the model development in the another studies. Then this figure compares the seasonal variation of ozone with ozone sonde measurement at northern and southern mid-latitude. So the old model shown by dashed line underestimated ozone at northern mid-latitude in the lower troposphere in the both hemispheres. Then in the middle and the upper troposphere, model biases are largely different among the models. Then the data simulation improved the agreement with the ozone sound measurement, and it also improved the multimodal consistency. So as shown by this the blue shade, that is the multimodal spread of the data simulation analysis is really small for any season for the entire troposphere. So we obtained a consistent ozone analysis using different model. Then this is a comparison of surface CO with the ground in situ measurement for the 4 models. So all the models shown by blue line underestimate carbon monoxide concentration in the northern hemisphere by up to 70 ppb, and also in the tropics by up to 60 ppb. So those model biases are also greatly reduced by the data simulation. Then this is the global distribution of the tropospheric OH. Then the annual mean OH concentration is reduced by up to 30% in the northern hemisphere in the geoscale model, and it is increased by up to 50% in the southern hemisphere in all the models. So these changes in the OH are associated with the changes made to ozone, shear, and NOx in our multi-constituent data simulation framework. Then the multimodal spread of tropospheric OH is also reduced by data simulation over most of the polluted regions, with up to 50% reduction in the spread. So which suggests that the multi-constituent data simulation framework provides the similar representation of the tropospheric hemisphere system. Then here is the north to south gradient of OH in the 4 modeling systems. So in all the systems, the ratio is decreased. Then with the mean model mean value of 1.29 to 1.18. So those are the significant changes in the OH are important in propagating the observational information among the different species, and also in modulating the chemical lifetime of many species, so which should be useful for emission estimate. Then we compared the a posteriori emission estimate of NOx in this case. And the global total a posteriori emission changed from 39 to 52 among the model. Then there's some standard deviations estimated for the industrialized and the biomass regions. So those the standard deviation information should be useful to suggest the possible uncertainty in the current top-down emission estimate because of the different chemical mechanisms implemented in different models. Then as you see here, there's some differences among the a posteriori emissions, but those multi-model analysis commonly suggested the potential problems in the bottom-up emission inventories, such as the too low summertime soil emissions, especially northern mid-latitude, and missing the open biomass burning emissions in India, and there's some the systematic biases in the biomass burning emissions over Africa and South America. Then using that developed multi-model framework, we have conducted the multi-model decadal chemical reanalysis for the past 14 years. And we are going to use this framework to study the long-term changes in atmospheric composition associated with human activity and emission changes. So this is the conclusion. We introduced the NOMOCHEM system. It provides the integrated unique information on the tropospheric chemistry system, including the precursors emissions. And there are some ongoing and future applications at JPL using this system, as listed here. And we are interested in applying this system to the GCHP and the WAP-GC system in the future to have more application and to contribute to the science application. Thank you very much.
Have you got a chance to look at the evolution of OH over years?
Yeah, we investigated.
How does that look like?
There's some increase in OH as a global mean over the past decade. So that can be attributed to the decreased NOx and some other CO emission trend. And that's a topic we have been working on using this system.
if I'm understanding properly, you're stitching together information from multiple satellites that look at NO2.
Yeah.
Do you have to apply any corrections to make sure the data products are consistent from one instrument to the next?
Okay, yeah, so we assimilated the NO2 measurement from OMI, OM2, and schema key. And there could be some systematic biases within this measurement, but we use the NO2 data from all the European products. They use the same retrieval algorithms, and we don't expect large differences within, large biases within those data. But over pass time is different between those measurements. So we optimize the diurnal variation of NOx emission using by combining those multiple NO2 measurements. So that's a way to combine the different NO2 measurements in our system.
Thanks, Hasu, again. Our next speaker, last speaker of this session, before we get to the poster instructions, is Katie Travis, who is now at MIT/NASA.
I just moved to NASA Langley. This is work I did with Colette Heald at MIT, looking at the ATOM observations to see what they could tell us about concerning modeled remote oxidation capacity. And a couple people have sort of touched on this already today, that models have trouble getting the global mean concentration of OH, and this means that the methane lifetime is wrong in most models. And so I'm showing here 8 different models and the methane lifetime, monthly mean methane lifetime, and all but one of the models have too low methane lifetime compared against observations derived from methyl chloroform. Here's GeoSchem in this dashed red line. So we fall within all these models that we have too much OH generally that keeps getting higher and higher, and too low methane lifetime. We also have a CO bias, and a lot of the CO is coming from oxidation of methane, most models also have a CO bias, as we just saw also, is an ongoing problem. So Steve laid out ATOM for us this morning. It was a perfect campaign to look at how well we're doing in the remote atmosphere and oxidizing methane and producing CO in the models. I'm using ATOM 1 and ATOM 2, which is the summertime Northern Hemisphere and wintertime Northern Hemisphere in 2016 and then 2017. And there was a suite of chemical measurements that Steve described earlier to test the oxidation capacity, how well the model can capture the remote oxidation capacity in this region. So first we had OH from Bill Brune on the GC8, and there's been a lot of problems with having OH in field campaigns in previous missions. They've done a lot of work trying to remove interferences and biases in the measurement. It's a very uncertain measurement, about a factor of 1.32, but we can compare against our model with more confidence than we could before. And we don't see problems in either the seasonality or in the interhemispheric ratio, which was just mentioned as another problem for models, that we have too much OH, it seems, as derived from methyl chloroform ratios in the northern hemisphere to the southern hemisphere. So we don't see that problem in the remote atmosphere. And we also compare well against the observations for both campaigns. But again, the measurement uncertainties are large, and there can always be compensating biases. So we have all the different drivers of tropospheric OH from ATOM. We have ozone, we have water vapor, and we have the photolysis. Frequency of ozone calculated from actinic flux measurements. I'm not going to show you those. Those look really good. MER2 looks great. Photolysis looks great. Ozone looks great. One thing that does not look great that enhances OH production is NOx. I'm showing you NOI. There's some trouble with whether we could use the NOx measurements. And NOI has an interesting problem in the wintertime northern hemisphere. NOI looks great in the summertime when we would have enhanced NOI in the upper troposphere due to lightning. In the southern hemisphere, we do pretty well throughout the troposphere. We might be missing a source of NOI potentially from the oceans. In the lowest few kilometers. But in the northern hemisphere, we have an over factor of 2 bias in the NOI, and this is entirely driven by nitric acid. And this is not exported from the continent. So uncertainties in the emissions inventories that we tested, potential biases, or missing trends are not accounting for why we have too much nitric acid in the remote atmosphere. And actually, it seems like the acid displacement so the sea salt uptake of nitric acid to form hydrochloric acid that Schwann from Danielle's group talked about could solve this problem. So as he talked about, this reduces OH, it reduces ozone. Our ozone simulation is currently in good agreement with observations in the remote atmosphere against ATOM, so we would need to drive ozone back up with a mechanism to not degrade the ozone simulation. Potentially, this could be done from the photolysis of particulate nitrate that Prasad has put into the model and tested to produce NO and HONO in the remote marine boundary layer with Thomas and Matt. I find that if I use that maximum source, I can drive ozone back up and improve the NOI simulation and some simple sensitivity tests and maintain a good ozone simulation. So potentially the effect of the sea salt on OH would be mitigated a little bit. The main point, though, is that the key drivers of OH in the remote atmosphere against ATOM are well simulated. But then what about the sink? So I'm putting the sink in terms of OH reactivity, so ranking all the different measurements from ATOM in terms of their concentration and their reaction rate with OH, and then looking at the lowest few kilometers at the suite of VOCs that react with OH, and then CO and methane and all those sorts of things. In the lowest few kilometers, because that's where most of the oxidation is taking place, and we also have OH reactivity measurements, but I'm not going to talk about that here. So these pie charts are showing the northern hemisphere and the southern hemisphere just for ATOM 1. ATOM 2 looks very similar. Of all the different components of calculated OH reactivity, methane and CO, as we know and expect, take up at least 50% of the OH reactivity and more in the wintertime. And the model's getting that, and we're getting the seasonality of this as well. What we don't get is the contribution of OVOC. So oxygenated VOCs are contributing over a third of the reactivity in the observations, and only a quarter in the model, and this is causing a low bias in our calculated OH reactivity, and this is almost entirely due to acetaldehyde. So this is something that was pointed out during PEM Tropics by Homwat Singh, and Dylan Millay wrote about it a couple years later in his acetaldehyde overview paper. And we see this again during ATOM, that we underestimate drastically acetaldehyde in the remote atmosphere. So this has been pointed out as potentially just due to measurement interferences. It's pointed out as possibly being incompatible with PAN. But however, we have a new measurement from the Caltech SIMS of peroxyacetic acid in the remote atmosphere that really supports that this acetaldehyde is actually missing. We need probably a remote diffuse source of VOC to produce this acetaldehyde. So peroxyacetic acid is made when what we call the PAM precursor, instead of reacting with NO2, reacts with HO2 and makes peroxyacetic acid. And so you can see that the bias in the northern hemisphere summer is enormous, just like the bias in acetaldehyde. And so actually we do need to figure out where this acetaldehyde is coming from. And I should just say that the measurement of acetaldehyde has also gotten much better too, so we have more confidence in that. I've tested a whole bunch of different ways of making acetaldehyde in the remote atmosphere, including adding a long-lived unknown VOC from fires, from the ocean, from anthropogenic activity. I've also tried out photolysis of organic aerosol. What I find is that the seasonality of adding this additional VOC can solve a wintertime acetaldehyde bias, but there has to be an additional source in the summertime. You can see that I can't really touch that northern hemisphere in the top left corner bias in acetaldehyde, even adding a really large perturbation of a diffuse long-lived VOC making acetaldehyde. Even with that amount of carbon putting into the atmosphere, which would produce, that would produce several to tens of ppb of this sort of unknown VOC. So this would be a really big deal if we could figure out what it is. Okay, so overall, the model simulation of OH and the remote atmosphere doesn't look like we have a serious problem, with the exception of the wintertime NOI, which we think we can solve. We're missing, again, this huge source of acetaldehyde, potentially due to unknown VOCs. That's been pointed out before, but we have new evidence to support that this is real. This also suggests that, so this diffuse VOC probably wouldn't solve our OH bias. This also suggests that maybe we need to look overland to solve our OH bias. With that, I'll take questions.
So the OH lifetime is very short. So I wonder how you consider the rapidity of OH inside the model gray box.
When I compare it against the observed OH?
Yeah, in reality, OH would have a kind of large gradient, horizontal gradient. So how would you, when you match the observed OH with model observation, do you consider the variability of OH?
I did not consider potential variabilities of OH within the grid box. That's also why I didn't just put up OH and say that the model is perfect, and that's why I went through and I didn't show you ozone and photolysis and water vapor and NOx, since it is such a short-lived compound. We can't just compare it against observations and say we're good.
Okay, so an objection to the acetaldehyde observations was a pan to NO2 ratio, right? That would be screwed up if you put in the acetaldehyde.
Yeah.
Did that change in ATOM? And a follow-up to that is, could you fix the acetaldehyde without screwing up formaldehyde?
Yeah. So formaldehyde, I changed. It's remarkably well buffered, and that's a mystery. This is formaldehyde. When I perturb with 100 teragrams of this mystery VOC, it really doesn't change, and that's a mystery. I also have pan. I'm not going to show it. Pan is not really sensitive here. I didn't look at the pan to NO2 ratio. It's not very sensitive in my simulations to trying to fix this acetaldehyde bias. And a study that just came out from the Toga group showed in a box model that if you constrain acetaldehyde, you need that amount of acetaldehyde to make the peroxyacetic acid. So if we trust the peroxyacetic acid measurement, we have to have that amount of acetaldehyde.
My question was,
You concluded that our OH bias must originate over land, but our bias is only 5 to 10%. So couldn't you accommodate a 5 to 10% bias within the range of the OH observations from ATOM?
Definitely. The OH measurement isn't good enough to constrain the remote bias. But if we trust how we understand the production mechanism of OH and the sink of OH, that wouldn't solve the problem. So if I go through all the production and the loss of OH in the remote atmosphere and trust that we're doing that correctly and we're not missing other things, I don't think we can solve it within the uncertainty of the remote measurements. There's also the interhemispheric gradient also that provides more evidence that we need to look over land.
Thank you. Now we have our poster introductions. I will ask speakers or poster presenters to line up here. We'll get this set up.
My name is Sabur Bure. My work is on constraining methane emissions in Canada using Environment Canada surface stations. I ran an ensemble of simulations to understand which wetlands parameterizations best reproduce the observations. I designed a custom tag methane simulation that isolated tracers by country, and inversion results showed overestimated biogenic emissions offset by underestimated anthropogenic emissions. Thank you.
Hello, my name is Frank Deng from University of Toronto. By using geoscale joint model, we inferred CO2 flux in tropical lands from satellite and surface CO2 observations, and then we analyze the flux against SIF and soil temperature. So if you are interested, please stop by our poster at C14. Thank you.
We use geoschem to simulate aerosols over the North Atlantic during the NASA's NAMES field mission. Here we use model version 11 with marine PUA emissions. We evaluate with modest AOD data and present some initial comparisons with ship and aircraft measurements during the first two campaigns.
Hi, I'm Kohei Ikeda from NIS in Japan. East Asia has a large contribution to the Arctic black carbon, and I use geochem to examine 11 transport events from East Asia to the Arctic, and we found 2 distinct transport pathways, Siberian route and Pacific route. And we also revealed that what meteorological conditions are important to these events. Thank you.
Hello everyone, I'm Shin, working with Professor Dylan Malay at University of Minnesota. Our project focuses on atom formic acid. So atom observed above 30 ppb formic acid, which is most probably coming from fire plumes. Among those fire plumes captured by atom, the formic acid enhancement ratio varies a lot from below 3 to above 100, 10 to the minus 3 mole by mole. So if you're interested in formic acid or fire, where the 30 ppb come from, is primary or secondary, how does the enhancement ratio varies, and how well are these captured by the model? So by my poster number 17.
Hi, I'm Eric Luch from the University of Toronto, and my work mainly focuses on the use of ground-based measurements from the NDAC network of CO and other biomass burning tracers, and we've implemented the GeoSchem chemical transport model that takes CO simulation to interpret our measurements and provide a means of source attribution. Thank you.
Hi, I'm Christian DiMaria from the University of Toronto. In the GeoSchem adjoint, biogenic isoprene emissions are calculated as a product of different Megan emissions factors, which depend on things like temperature, sunlight, leaf area, and leaf age. Top-down estimates of isoprene over the North African savannas have found a twin peak seasonal cycle with 2 local maxima. We've reproduced this cycle in the GeoSchem adjoint and found that it's largely driven by the rainy season. If you're interested in finding out more, please stop by poster C19. Thank you.
One last final round of applause for all the speakers in this session. We're applauding you for giving us the lunch on time.
And we will reconvene at 1:30 right here for our first year quality session. See you then.